Okay, good morning, all. I hope all you're doing well. Today we are going to run a new subject and the last subject of the course, and we will complete it today. And next week we are going to solve a few mixed problems regarding all the subjects that we talked so far. Let's get started. The main subject today is the buckling. Okay, here we go. Subject is buckling is the behavior of the structural members under axial compression load. Okay, we will check this buckling under compression load. So what is important here? We need compression load, not tension. Okay, we have to squeeze the structural member, column, a strut or whatever. Not we apply a tension and make it straight. Okay, we squeeze it. Under this compression load, what we have to get to make a good design, our stress should be, by the way, less than allowable stress. And also here, there's a critical thing, which is the delta L. The change on the length of the member should be less than the allowable length change. I will explain it. To talk about the buckling, we need to talk about the stability. To explain the stability problem, we have three cases. The first one is a bowl. A bowl we have like this. This is the ground. It has this shape, and on this ground we have a ball. Okay. If we move this ball in this direction or in this direction and make it free at this level, how it goes? It goes back to initial position. So, okay, we can move it to left and right, but it comes back to the initial position. So we call this type of balanced position stable. This is stable. Okay, so we can change the location, but it comes back always to initial position. It stays like that. This is a stable equilibrium. The second case is here. We have an uphill like this, not a bowl. So this is again a ground. On top of this hill, we have a ball again. At initial position, it has a balanced position. That's okay. When we move it left or right, so it's gonna go all the way down to the heel, so it can't come back. So its balanced position is completely changed, and the balance is broken here. So this is the unstable case. So in the first case, okay, we can change the location of the ball, but at the end of the day, it comes back to its balanced position at the bottom of the ball here. But in this example, we have a uphill at the top of the hill, we have a balanced position. So when we move it, the balanced position completely change. We break it down, we can't get this balanced position again. So the ball goes down and the balance situation is completely changed. So we call this type of situation unstable. Okay, unstable. There is one more example here to explain this. This is the ground. It's a flat surface. And on the ground, we have a ball again. Okay, this is a flat surface. If we move this ball right or left, it's always again in the balanced position on this level. So this balance doesn't change. Okay, the location, it can move from here to here. That's okay. But at the end of the day, here again, it's in the balanced position in the same level. So this is this movement doesn't change the balance position. So we can call this behavior neutral stability. So neutral means no change on its stability. So these are the balance definitions for the backlink, for the members under the compression loads. For example, if we have a T ruler, sorry, okay, we have the centimeters and numbers here. If we apply, look at this T ruler from the section. So if we apply a compression here, it's gonna get shape. It's gonna get this curved shape. And so when this ruler gets a certain amount of compression, it's gonna fail. Okay. This is the compression capacity. Okay. If we apply tension in the second case, we have a tension load. Okay. By the way, this is compression, this is tension. So let's say it fails under tension. It's broken down from the mid portion under tension load. If we compare the tension load capacity and compression load capacity of this ruler, what we will see, the P tension really greater than P compression. At the end of the day, we have the same material, same member, but the behavior of the members under tension and the compression completely different. Under compression, as you can see here, we will change our balanced position. So it's gonna get a curved shape like the green arch here. So when its shape is changed, we know that the capacity of the member changes and it gets reduced. But in tension, it's almost in its initial position, as you can see here. So we increase the tension step by step, and okay, it fails at the end of the day, but the capacity load at tension is really greater than compression. Today we are gonna actually, this part, how to deal with. We talked about the axial force effect on the structural members. In this axial force case, we only talked about the tension loads. Today, we will deal with the axial force case, but this force is compression, and we will talk about this shape change, and we will calculate the compression capacity of the members. To do that, we have a theory, Euler theory. Let's talk about the Euler's theory. It helps us to calculate the capacity of the compression members. It looks like a little bit complicated at the beginning, but I will give you, I will find actually a generic formulation at the end. And if you understand how to use it, actually, you can calculate the capacity of these members. Okay, the subject is here, Euler's theory. To do this, to explain this theory, I'd like to talk about the assumptions at the beginning here. We have some assumptions. The first one, we have actually 1, 2, 3, 4, 5. 5 assumptions. What they are? The frame member or structural member is perfectly straight at initial position. So it's perfectly straight. There is no imperfection on the member. Okay. Perfect straight. Sometimes we may have the imperfections. Bazı kusurlarımız olabilir gerçekte. Şöyle olabilir mesela. It's really small amount of imperfection, but what we assume that our member is perfectly straight. There is no imperfection. The second one is the material is, by the way, let me clear this part. Oop. Here we go. The material is completely homogeneous. Okay. And structural member is under the axial load. Under axial load only. And the stresses on the member, structural member, versus on the structural member are less than proportional limit. I will explain what is this. Remember, if you recall the stress strain diagram of the steel, it is like this. The stress behavior is linear till this proportional limit, sigma proportional. So what this assumption says, the stress is less than proportional limit. Stress is in this region. So in the next assumption, I will say this assumption again. Hooke's law works for the member. So if our stress is less than proportional limit, that means we are in elastic region. We are in elastic region. So it's linear, and also this portion is linear elastic because it's like a line. So if we are this linear elastic region, remember the Hooke's law, which is sigma. By the way, this is sigma, this is epsilon. Stress, strain. Here is stress, you know. Hooke's law says E times epsilon, Young's modulus, this is strain, this is stress. So according to the Hooke's law, there is a linear relationship between stress and strain, because this E is the slope of this linear region. So we are, according to these two, we are in linear elastic region. Okay, don't forget this one. According to these two assumptions, if we go beyond this linear elastic region, okay, we can do calculations, but the method is not the Euler's theory. We will learn it today, but now we are just talking about the Euler's theory. Okay. Okay, I'm gonna calculate draw a sketch, by the way, to explain the case. Yes, this is my perfect straight member. Okay, perfect straight member. At the bottom, I have a pin support. At the top, I have a pin support too, but it can move in vertical direction. This point, as you can see, I have drawn here two vertically roller support, as you can see. This point, this top point, can move in vertical direction. And here, the length of this member is L. This is the first case. In the second case, when we by the way, we are applying P here. This is the compression node. When we apply this here, okay, here we go. We have P again at the top. When we apply this P, as you can see here, we are at this level. Our top point goes a little bit down. So when it goes down, our structural member gets this curved shape. Okay, curved shape. This shape is again neutral axis case. Neutral neutral equilibrium. Or yes, we talk about the neutral equilibrium. We can change its location, but it's again in the equilibrium condition. This is neutral equilibrium. So, but if we increase the P load, at the end of the day, this member fails under this compression load. That's okay. Now we will write the equations to calculate the compression loads. I'm gonna draw. This is X. This is Y. Okay. And here, in this case, this direction is X, this direction is Y. This position is support at the bottom. And I cut the member and take it out here, the curved member. So here we have Y, and here we go X for this point. At this point, what we have vertical load and also a moment. Why we have a moment? Okay, in the neutral equilibrium, we can write these laws. Our midpoint goes right a little bit to this position. So there is an eccentricity here. When we change the location, remember, when we shift a force to somewhere else, we add its moment there. This moment comes from there. Okay, let's write these equations. M here equals P times Y. So Y, if we write the equations, I, so at the end of the day, this is gonna be like M is P times Y over EI. So it's minus. Okay, it's minus. I'm just trying to get the last product, the last formulation. You don't have to memorize all these mathematical steps, but the result is important. But I'd like to show you there is a logic why we are getting these formulation. The curve y plus p over ei times y equals 0. So if we say p over ei k square and go here, I over plus k square y equals 0. So y here c1 times x plus c2 for to solve this equation, we can talk about the boundary conditions at x0, y is 0 here at this position. So if xl at the top of this member, again there is no lateral movement, y is 0. These are the boundary conditions. So if we use the first boundary condition here, by the way, from the first boundary condition, c1 equals 0. So y is c2 times sine kx. Okay. So c2 not equal to 0. Oh, by the way, sorry. For c2 not equal to 0, sin kl equals 0. From here, kl and p. So k square l square, if we take the square of the left and right sides, and square p square. So remember this part, k square was p over ei. Let's put it over here. P over el, ei over l square equals. Yes, this is equation. From here, if we get the p from this equation, p is n square p square ei over l square. So here and for n equals 0, p equals 0. For n equals 1, p goes minimum. So here, what you're going to do? P critical equals p square ei over l square. Here, instead L, we put L LK. What is LK? LK is buckling length. I will explain. Buckling length. So the critical force is at the end of the day is P critical. P square EI over LK square. Okay. Well, this is the critical force. You have to know this equation, critical force, which buckles the structural member. Here, we know P is P, you know, E is modulus of elasticity, I is moment of inertia. The only unknown here is LK, which is the buckling length of the member. Okay. So if we go back to the, how can I go back? First page. If you take a look at the equation, or not equation, that take a look at the sketch, by the way. In the sketch, our structural column has two hinges at top and bottom. As you can see, we have two hinges. One for top, one for bottom. The hinge means, you know, there is no moment at this point. This is the first one. This is the second one. So this Euler's theory is, this theory works for actually only two hinged members. Okay. But in real life, we have different support types. We may have fixed support, we may have cantilever member, whatever. So how we can convert all these buckling lengths to this one. So here we are dealing with two hinged members. Okay, let's go back our page. I will explain it now. We have 1, 2, 3, 4. Yes. One. 3 and 4 members. All the members have same length, which is L. Oh, by the way, I'm sorry. I put the fixed support to all of them. I'm sorry. Okay, for the first one, we have fixed support at the bottom and free end at the top. Okay. If we apply the compression load on top of this one, what is the buckling length of this member? Because we are going to use this equation, but we don't know LK. It's easy. There is a logic behind that. I will explain the logic. If you don't understand the logic, you can memorize these numbers. But what I suggest you not to memorize. If you understand what it is, you don't need to memorize it. So it gets this shape. Okay, under node P. So at the end of the day, as I explained at the beginning, our equation works for two hinged member like this, and this two hinged member gets this full arch, fully curved member. From this support to this support, it gets a arch shape. Can you see this one? Yes. So I need to get this shape for each case. For example, for the vertical cantilever, can I do this? If I complete this red curve to a total fully arch shape, this one. So what I get here, I guess this is L, this part. To get the fully arched shape, I need one more L. So LK for this vertical cantilever is 2 times L. The buckling length for the vertical cantilever is double L, as you can see. The logic comes from here. I have a deformed shape, but at the end of the day, I convert this shape to the double hinged members shape. So it's a fully arched shape. If I complete this half arch to the complete total arch, I will get double L. Let's take a look the second one. The second one is same as the double hinged one. Double hinged, this portion is roller, it goes down. So here we have a hinge at the bottom, here hinge. When we apply this load P, we will get this one. Total curve. So this is L. In the other one, here, if we have a fixed support at the bottom, and at the top, if we have a roller support, we will have a shape like this. So what I'm looking for here, I'm looking for a total curve like this. Total curve in this shape, in this curved member is from here to here. So when we look here, the buckling length should be less than L. So it's 0.7 L. The other one and the last one, we have a fixed support at the bottom. We have a fixed support at the top. So fixed means we can transfer moment from this support, but it can move in the vertical direction to get the buckling. So what we will have, okay, we will have this shape. So let's find the two hinged members shape. total curve, where it is. It's here. It's in this portion. In the previous example, it was like this. So when we take a look at this shape, we need this length for buckling length. This is less than the previous one. It should be 0.5 L. Okay. LK is this. Okay. The logic of LK comes from here. I think you can memorize it. That's okay for different support conditions, as you can see here. But here, don't forget this one. This is fixed. Fixed and roller in the vertical direction. This is pin. This is pin. Okay. This is the free end at the top. You have to know these buckling lengths. It's important to solve the problems in this case. Okay, we're just talking about the critical case, critical load. Now I will a little bit talk about the critical stress. When we talk about this critical stress, we will see where this Euler's theory works and where it doesn't work. And if it doesn't work, what can we do? Can't we solve the problem, or is it easy to solve problem? Okay, we will see it. Let's talk about the critical stress now. Here we go. Critical stress, kritik gerilme. When we are at the critical load level, that means we have the critical stress. The sigma critical is P critical over A. This is the basic equation that you know for stress. Force over area. Okay, what is the force here? P square EI over LK square. This is the force. And if we put here the area, so force over A, we will get this one. So this portion is P critical. And here, if we make an arrangement on this equation, what we will see? Do you remember this? Small I. What is it? Small I. You may remember this from the statics course. I is kök square, sorry, I over A. Radius of gyration. Atalet yarıçapı. If we consider these two, So this is I square. I'm sorry. I square. Instead of I over A, I just put here I square. So here, uh, critical stress is, if we take this I square, the bottom side, LK over I square. We are gonna see a new definition for this part. This one. Lambda is LK over I. What is lambda? Slenderness. Slenderness is in Turkish narinlik. Okay. Buckling length over the radius of gyration gives us the slenderness. Okay. So critical stress here. Here. And lambda square. This is the critical stress definition. Here, this is the critical stress. But at the end of the day, if you multiply this area, you are gonna get the critical force, P critical. Okay, so everything is coming from here. Now I will explain where this works. Okay. Okay, this is the critical stress. And this is the, yes. Here, sigma critical and lambda. Lambda is slenderness, remember. The Euler's hyperbola is like this. And what we know, here we have a limit, stress limit. What was it at the beginning? We talked about that. Our stresses must be less than sigma proportional. So if here is sigma P, we should be less than here. So according to this, oh, by the way, I'm sorry. The Euler's hyperbola works for this portion. Yes, this portion. What we have here, we have a lambda limit. So if our structural member more slender at this side, the lambda gets bigger, so it gets slender, more slender. Euler's hyperbola or Euler's theory works here. But if our slenderness is less than this limit slender, that means the stresses are not under the the how can I say, yes, the system or structural member doesn't buckle. So if our slenderness less than this limit value, we are going to use a different method, because Euler parabola goes like this, but here it doesn't work. We will use a different method. We have two methods to do it. I will explain now. We are going to talk about Tetmayer method or Rankin's method for this portion. Okay, for this portion. For the parabolic sides, if we are having a slenderness higher than this limit, this is, let's say, lambda p, we will have the Euler's theory. So let's draw one more sketch to explain it again. Okay. Again, the vertical one is sigma critical. This is lambda. Here, the method is like, after this move, like this. So here we go. This limit is lambda p. This is sigma p. If we divide the left portion to two sides, generally, if the lambda here is around 40, the smaller portion is called for, this is for short members. Short members. Okay. And our limit lambda should be around 120. It may change. For example, it may be 110, 100, but it's around 120. This portion is for midline. Middle members. And if our lambda is greater than this limit, lambda p, this part is for long members. So long members buckle. So here Euler's theory works. For this portion, the flat line, straight line portion, we use two different methods. You don't have to memorize the equations. If we are going to use it, we give these equations in the exam and in the example questions. Okay, we give it. But you have to know when you can use it. The first one is That Myers method. Here we have critical stress. For this critical stress, we have an empiric equation, C1 minus C2 lambda. For steel, sigma critical equal minus, okay, here this equation is, unit is this. When we use it, if our lambda less than lambda p equals 105 for timber, because these equations change according to the material. Sigma critical equals minus, we use this equation when lambda less than lambda p equals 100. Okay. As I said to before, you don't have to memorize these numbers, but you have to know when you are gonna, we will give these equations, okay, for you. You don't have to memorize it. You should know only that when your lambda, you're going to calculate the lambda slenderness. If it's less than lambda p, okay, use this method. If it's higher than this lambda p, use the Euler's theory. Okay, we will check it. Then we are going to select the method. Okay. Oop. The second one is Rankins formula. We have one equation for steel. The general equation is like this: C1 over 1 plus C2 lambda square. So for steel, the sigma critical is 3000 over 1 plus 0.00077 lambda square. Again, you don't have to memorize this number. Okay, memorize this number, and we will give you when we use it. Okay. Actually, this is the subject today. I will explain the section check in the second session. Then I will solve a few. Actually, we have time. Can explain it. You see how many examples we have. Okay, let's complete the section check, how we check the sections. Then in the second session, we can solve only problems. How we check sections. Okay. If we know the LK, we know LK, the buckling tent, and then I mean the minimum radius of variation. Why we are dealing with minimum, I will explain. Calculated I minimum check the moment of inertia for both axes and take the minimum one over A. So we get lambda LK over I mean. So if we get the minimum I mean, for sure, we are gonna get the maximum lambda, maximum slenderness. Okay, don't forget this one. So if this is minimum, we will get maximum here. So now we know the lambda, and what we will do, we will check if lambda less than lambda p or not. If this works, calculate sigma critical from empirical formula. One of these methods, Ted-Myers or Rankin's methods. Okay, according to what's given in the question. Okay, lambda less greater than lambda p. To solve sigma critical, use Euler's theory. So what we will do, P critical, sigma critical times A, put here the sigma critical, what was it? P square E over lambda square. So P square EI over LK square. Okay, LK square. So we have P critical now. So this is not actually, this is the buckling load, that's okay, but we have to consider a factor of safety here. Factor of safety, what we don't make our check directly according to the calculated critical load. The allowable load here is P allowable is P critical over N, factor of safety. It's the N is given to you. It depends on the question. Actually, the N must be greater than 1, by the way. But generally, it's 2, 3. Okay, in professional life. So here we can calculate the allowable load. This is the capacity of that member. Let me see what we have here in my notes. Yes, this is the method to design the structural members under compression. So it's 10:15. Let's have a break. In the second session, I'm gonna solve you 3 or 4 questions regarding this issue. I guess you're gonna get better understanding of all these equations, and you're gonna understand how we use them. Okay, see you guys in the second session. We are gonna be here at 10:45. Okay, 10:45. See you guys. Okay. Now we are gonna solve a few problems regarding the buckling calculations. Okay, let's get started. By the way, let me check. We are recording, yes. Okay. Examples. First one is, so we have a vertical cantilever section. Its length is L is 6 meters, and the section here is circular section. Yes. This is the circular section, and the diameter here is 20 centimeters, and here the thickness of the circular section is 2 centimeters. Modulus of elasticity here 2.1 times. If lambda less than lambda p equals 120, the method is here. The n 2.5. According to all given data, what is the p allowable? N is, remember, factor of safety. Okay. What we are gonna do here, we need to know the slenderness, actually. Slenderness, because according to the slenderness, we are gonna select our method. If our slenderness less than lambda, the calculated slenderness less than lambda p, we are gonna use the equation given here, which is an empirical equation. That's it. But if it's greater than this lambda p, at that time we are going to use Euler's theory. You have to know the Euler's p critical equation. Okay, you have to know that. We are not going to give it. We only give this Ted Myers or Rankin's formula in the question. To find the slenderness, remember what it is. Lambda K over I. LK is buckling length. You know, here is the radius of gyration. This completely depends on the section. So we have to calculate the, by the way, this should be LK mean. It directly depends on the moment of inertia. So here, this is the equation. So here, since our section is a circular hollow section, in each direction we have the same moment of inertia. So we will get moment of inertia, then we'll calculate the radius of gyration. Here we go. It's wrong here. Just a second. In my notes, there's a problem. Oh, here we go. Yes, let's calculate the moment of inertia. This is for the solid circular section. So from here we can calculate the circular hollow section. The section is here, is only this portion. The mid portion is empty now. I equals for radius for total, then minus 84 equals this is the moment of inertia for each direction. We have to calculate the area, area. It's easy for you. P r square, r is 10. First one minus 8 square. So this is the area. Now, what we have? We have at the moment all information to calculate the I, radius of gyration. Let's do it. A. Okay, let's calculate it. Yes, here the radius is this one. Now we need to calculate lambda. LK. We have to take a look to LK. What is LK for this question? What kind of column we have? We have a vertical cantilever. Top end is free and bottom end is fixed. So remember, it's gonna get this shape when it's loaded, right? So we are looking for the total arch shape. This is the half of the arch. We need this one, this total length. This length is important for us. So for the cantilever, so double L is the buckling length here. Double L, so 2 times centimeter, 600 centimeter over I. Here the slenderness is this 187. The lambda is greater than lambda p here. So what method are we gonna use? We use the Euler's theorem. Okay. We make a decision here depending on the lambda. That's okay. we will use the equation, critical load equation here. P critical. Yes, let's do it. E is, what was E? Times I. I is given in the question. LK. LK square. So here, the P critical is this one, 66,741 kilogram. Is this our design load? No, we need to find allowable force, P allowable. Remember, we need to consider a factor of safety to get the allowable force, P critical over N. Here, the allowable, the factor of safety actually is 2.5 over 2.5. And here we will have approximately 26,700 kilograms or 6.7 tons. Okay, this is the first example. Any questions so far? Nope. Okay, let's use the same column with, let me, just a second. If L is centimeter for the first question, if L 350 centimeter, what is the P allowable? Okay, the shape is same, everything is same, support conditions are same. The only thing which is changed is the length of the column. Okay, length of the column. So we need to consider here the slenderness, slenderness again, because the section is same, so I is same. The only thing changes here, LK. Again, the backlink length is double L because it's vertical cantilever. So 2 times 350 over I here. I is 6.41, I guess. Let me see. Yes, 41. LK over I. So lambda here is, which is less than. So what we will do? If this is greater than 120, we use Euler's theory. Here we will use empirical equation, which is given in the question. Here we go. Sigma critical is, this is the equation. Now let's calculate it. Minus lambda is here. and sigma critical here is this 1,855 kilogram per centimeter square. Okay, that's okay. What we have now, we have the stress. We need to convert it to the critical force. So P critical equals sigma critical times area. So stress times area gives us the force times area. We calculated area over here. It's this one. Okay. So this is the critical load. Stress times area. Is this okay? No, we have to find allowable stress force, sorry, over the factor of safety 2.5 equals this is the P allowable. So in this question, we tried two methods. One is Euler's theory, other one the empirical equation. The only thing we changed in the question is the L. If the L changed, you know, the slenderness is changed. So the calculation method depends on the slenderness, you know. We have to find lambda. According to the lambda, we decide the calculation method. Okay, don't forget this one. You need to get lambda in each question. Okay, what we have here. Yes. Okay. Another question. Here we have a straight member. What? The pinned end. So here, let me see, by the way, what's it? Here the total length is 6 meters. For this member, I mean is given in the question, which is and also this one is given in the question. So if lambda less than lambda p critical, the loads are, the sigma critical equation is given here, and here 2.5. So what is P allowable? What is P allowable? So here we directly get the lambda because all these unknowns are given in the question. Lambda is this. So here, what is LK? The both end is hinged in this column. It's completely same as the Euler's column. Euler's column, two hinged column. So it gets a shape under compression load, like a fully, totally arch. So the buckling length is 6 meter. 6 meter. Over, I mean, 4 point. What is the lambda? Lambda here is around, I think it's like this, greater than 120. So we should use Euler's theory. This is the decision depending on lambda. So P critical. This is easy. You can do that. Okay. But to do it, you need to get the radius of gyration correct. Actually, it's not the subject of this course. It's coming from the statics. You have to know how to calculate it. You have to know how to calculate the moment of inertia. It's really important. Otherwise, you can't solve the problems. Okay. P square E I over L K square. Let's write the equation times, by the way, I can give E here. It's given in the question. Okay. It's a constant number for steel. Times I, given in the question again. LK is the length of the member, 600 centimeters square. So P critical over here. So P allowable here is it's around kilogram, not ton. Kilogram. That's it. Okay, we have the lambda. According to the lambda, we make decision for the calculation method, and we follow the method we selected. That's it. When we get the critical load, don't forget that we have to consider a factor of safety. We need allowable force, which is used for design. Okay. Yes, here we go. What we have now. Okay. Here, I'm gonna use a different type of question. Here we go. Yes. This is 3, I think. Here we have a square section, and also here the structural system. We have here roller, vertical roller. Hinged. Yes. Here we have a timber section. Dimensions are 12 by 12 centimeter. The allowable load for this system is P allowable is 6.3 tons. So, by the way, the other data given in the question is lambda. If this works for us, use the empirical equation, which is this for this question. N is 3.5. Modulus of elasticity, E is 10⁵, and sigma allowable. The question here is to carry the 6.3 allowable force, what is the length of member? The question is here. Okay. Now we are gonna go back. Actually, we are gonna go back to find the L. By the way, if this is allowable force, what is the critical force? Okay, what is the critical force? P critical. So P critical is N times P allowable. By the way, let's write the equation then. P allowable here is P critical over N. So if we multiply these two, we get this one. P critical equals 6.3 times 3.5. Okay. 3.5. So if you multiply these two numbers, we are gonna get critical force like this. Now we know the critical force, but we don't know which method are we gonna use, because to make decision to solution method, we need to have lambda, which is slenderness. It's directly depends on the length of the member. Okay, here what we will do, we will select, okay, we have two choices, Euler theory or empirical equation given in the question. What we will do, we will select one of them, and then we will, after we get the solution, we will check the lambda. If it's okay for that solution, yes, the solution is correct. If it is not, we have to follow the other solution. Firstly, let's do it. You're gonna get better understanding. We will select the Euler's method here first. Okay. Let's say our slenderness, we have a slender member and it buckles. So Euler's theory works for this equation, this solution. So let's do it. To Euler's theory, you know, P critical over L K square, you know. So what we need for this equation here, we need this one. Okay. We know this one. We know this one. Actually, from section, you know, I. Okay. This comes from here. This is I. This is I. Okay. Let's put I here. This is critical. Critical load here is E is I is. Okay, here we are gonna put buckling length here. Okay, we don't know the total length, but what is the buckling length for this support condition? The top is, you know, pin, bottom is fixed. If you take a look the chart I gave you in the previous lesson, you're gonna see that the curved shape is like this, and the buckling length is defined as the total arch. It's almost 0.7 L. Okay, here we are going to use 0.7 times L. Here is square. Now, the unknown is here, L, you know. If you solve this equation, you're gonna get L is this, 397 centimeters. Now we have the L, but we have to check if our assumption at the beginning is correct or not. We need to check lambda because we assumed that our lambda will be greater than 70. That's why we used Euler's theory. We should check if it's greater than 70 or not. Now, let's do it here. Lambda is LK over I. Okay. Here, actually, do we have I here? No, we are gonna calculate it. Oh, here, lambda equals LK 0.7 times over I is, you know, this is I. Over area. Area is the square root of this one. this equation. Okay. And if we do this equation, lambda here is 80. Is it greater than given limit? Yes, it's greater than 70. So Euler's theory. It's okay. We did a good job. Okay, we made a calculation here, lambda. We get, for example, 50. At that time, our solution is wrong. We have to go ahead with the empirical equation. We have to follow the same methods with empirical equation. After we get L, again, we should check the slenderness to verify our solution is correct. Okay. Now, this is the example. We have another example here. Yes, I guess. Okay, let's solve the last example for today. I have one more. This is the fourth example, yes. Here is the section. We have a box section. Okay, this is the box section. So the sizes are given here. 5, 15, 5. In the vertical direction, here is 5. The wall thickness is 5. This portion is 30. And we have two axes, y, x. Okay. And the structural system for this section is like, here is a pin support, top is a pin support, okay. The total member length is 9 meters. Here is lambda. This, if lambda is less than 70, sigma critical is minus this one. E is this one. N is 3.5. This is the factor of safety. Sigma allowable for the material. Okay. So calculate the allowable force. Okay. Here the method is always same. You have to get lambda. To get lambda, we need minimum minimum radius of variation. To get the minimum radius, we need minimum moment of inertia. As you can see here, we have two axes, x and y axis. We have to calculate the moment of inertia according to these two axes, and we need to get the minimum one. Okay, this is gonna be a recap for you. I assume that you know very well to calculate the moment of inertia, but I will write the moment of inertia equations again here. Ix the method is same. You have to just make these calculations correct. That's it. Okay, this is for the Ix. Okay, Ix. And let's do Iy. This one. Yes. Please calculate these Ix and Iy by yourself, by your calculator. Do it as a practice. Okay. Area. We need area also. We are just calculating the sectional properties at the moment. We are not doing anything about the buckling capacity of the forces. These are all about the sectional properties. So from here, we need to get I mean, which is Iy, as you can see here when you compare this one and this one. Yes. So radius of variation is here. Okay. Now we have the minimum I. So we need to calculate the lambda LK over LK. What is it? Top support is roller support. The bottom support is, sorry, pin vertical roller. This is pin again. So it's gonna get the shape like this. It's Euler frame. So the L is L itself, 100 over here. Equals, what is lambda? Okay, here, according to this one, we need to use Euler's theory. Okay, Euler's theory. Let's do it. P critical. Yes. What is I? I is, I mean, you know, over 9 meter square. So from here, P critical is P allowable is is considered a fake factor of safety, and it's gonna be 15,000 kilograms. Okay, this is the P allowable. P allowable. Okay. Yes. If here the length of the member, let's change the, this is the fourth question, this is 51. If we are gonna use the same previous example, if L is 20 meters, what is P allowable? Okay, let's go back. The only thing we change here, because till this part here about the sectional properties. Okay, we make decision here. Let's calculate lambda. Lambda equals LK over, LK is here. What is here? 8. Okay. Lambda is 58.4. So that means empirical equation works for us. Yes, we will use the empirical equation given in the question. What was it? By the way, let's go back. Critical is minus lambda times. So sigma critical here is okay. This is sigma critical. We are looking for P critical because we are dealing with force. Stress times area here, area is here. Okay, here the P critical is up. This is P critical. We need P allowable. Okay. If we divide this to 2.5, which is the factor of safety, we are gonna get this one, 28,240 kilograms. So this is the allowable force. We should check this force. This is the capacity of the given member. We can calculate the capacity. We can check the loads given on the structural system, if it works or not. To decide it, we need to find the allowable force and compare it. If we have a force greater than allowable force, the system will fail. It doesn't carry that load. The given load should be less than the allowable load to carry it safely. Okay. Okay, actually we solved 5 different examples. These are all examples regarding the subject. Today we completed our subjects. Next week is the last session we are gonna do before the final exam. Please join the class. We will solve the examples. If you have time, please take a look all these subjects. If you have any question, please come to class with your questions. We can discuss them. Yes, that's all for today. Thank you for your attendance. Take care of yourself. Have a good weekend, guys. Okay, bye-bye.